Good afternoon, everybody. Let's get started with the central limit theorem. That's where I stopped last time. Let me go ahead and remind you of the basic conclusions of central limit theorem, CLT, central limit theorem. If your sample size n is greater than or equal to 30, okay, then conclusion number one is mu sub x bar is the same as the population mean. That means mean of the sampling distribution is the same as the mean of the population. Then the next conclusion, which is conclusion number two, standard deviation of the sampling distribution is the same as the standard deviation of the population divided by the square root of the sample size. So these are the two conclusions. Now, this is case one, okay? This is case number one. And case number two is what if n is less than 30? In that case, what happens? Do these properties still hold true? The answer is yes, it does, but under certain circumstances. First, the population from which you are sampling, if it has bell shape, the population from which you're sampling, if it has bell shape, okay, so population normal, that means sampling distribution is going to be normal too. And both of these conditions will hold true. That means mu sub x bar is equal to mu and sigma sub x bar is equal to sigma over square root of the sample size or square root of n. And it doesn't matter what the sample size is if the population from which you're sampling is normally distributed. Now, let's go ahead and talk about sampling distribution a little bit, just to make sure that you guys are okay. Our example was very simple. All right. We had 100 students, okay? 100 students in a class, and we want to select groups of 30, okay? 30 students. How many different ways can I do it? As it turned out that it's like 2.9 times 10 to the power 25 different ways, to approximately 2.9 times 10 to the power 25. Literally, as I said, this is infinity for practical purposes. This number is so huge, okay? So many ways you can select groups of 30 different students, okay? So many ways you can select these groups of 30 students. Now, for each of these groups, okay, for each of these groups, if you were to find the average, so let's say for the first group, the average is x1. For the second group, the average is x2 bar. For the third group, average is x3 bar. And if you keep doing, and the last group, let's call it xk, okay, xk bar. If you were to consider all of these, there are so many averages, right? And you find the distribution of them, that distribution is going to be bell-shaped. That's the sampling distribution. This is called the sampling distribution. Remember, sampling distribution is the distribution of the sample means. Now, this is a distribution in and of itself, so it must have a mean, and that mean we denote by mu sub x bar. And this is a distribution, it should have a standard deviation as well, and that we denote by sigma sub x bar. These little x bars on the side, lower right, is indicating that we are dealing with sampling distribution. In this particular case, our sample size was 30, okay? We are selecting groups of 30 students from a group of 100. All right, and the conclusions of the central limit theorems, as I have written here, as well as here, is gonna be mu sub x bar, that means mean of the sampling distribution is the same as the mean of the population. Here, please keep in mind, mean of the population is when you have a sample size of 1. If it is anything greater than 1, then it's a sampling distribution. Mean of the population is associated with sample size of 1. Okay. And the second conclusion is that sigma sub x bar is equal to sigma divided by the square root of the sample size. Sigma divided by the square root of the sample size. Now, these are the conclusions of central limit theorem. Keep in mind two special scenarios. When n, or the sample size, is greater than or equal to 30, it does not matter what the distribution of the initial population. The sampling distribution is always going to be bell-shaped, okay? If your sample size is bigger than or equal to 30, initial population's distribution doesn't matter. It could be any arbitrary distribution. The sampling distribution is always going to be bell-shaped with a sample mean is equal to mu and population mean is equal to, with the sampling distribution mean is equal to the population mean, and sampling distribution standard deviation is the population standard deviation divided by the square root of the sample size. Is it okay, guys, so far? Am I going too fast?
Yeah.
Yeah, it's all right. You guys are comfortable with these ideas?
Yep.
Yeah.
Okay, good. Now let's go ahead and do some problems. I'm gonna clean up this. If you have the slides open, I'm on page number actually, I'm gonna do the problem that I did last time, and I'm gonna let you work on another problem. So everybody, please pay attention. Everyone, I want you to know these materials because this is gonna be on the midterm, it's gonna be on the final, and these are really important stuff. Central limit theorem and the sampling distribution and all those concepts, because we are gonna be doing hypothesis testing and confidence interval. Both of these ideas are central to the statistics, and they depend on the concept of central limit theorem. So if you have a good understanding of the central limit theorem, you can think of this as the foundation, okay? That will help you understand the rest of the materials. So the problem was Mr. Zuckerberg, so slide number 129, okay? Slide 129. And as I said at the beginning of the semester, we'll probably have about 250 slides for the entire semester. So I am there right now. I think I have probably 159 or something. So Mr. Zuckerberg, the founder of Facebook, recently announced that an average person spends about 50 minutes per day on Facebook, Instagram, and Messenger. Assume that the time spent on these social media networks are normally distributed with a standard deviation of 30 minutes. So it's bell-shaped, they tell you, with a mean mu, population mean is equal to 50, and population standard deviation sigma is equal to 30. Okay. First, what is the average number of minutes that a person spends on the social media channels? What is the average number of minutes that a person spends on the social media? Which is pretty easy. That's just mu, right? Okay. Mu is 50. The next question, what is the standard deviation? Which is also simple. Sigma is 30. So standard deviation is 30, mu is 50. Okay. Now, the next part of the question. Now, if you take a sample, so this is where you want to start to pay attention very closely. Now, if you take a sample of 25 people, so there's your n is equal to 25. If you take a sample of 25 people who use social media, then what is the average of the sampling distribution? Now, we are not here anymore. We are not here. Here, the population, we are dealing with sample size of 1. Like the questions, last two questions asked, what is the average amount of time that an individual or a person, just one person, spent? However, Here is 25 persons. So the average has to be a natural choice for it. You cannot ask for one person. It's 25 people, their average. What is the average of the sampling distribution with sample size 25? So now this is where I kind of would like to ask you a question. So there's the sampling distribution, which is sample size of 25. Sampling distribution with sample size of 25. Mu sub x bar is equal to what they want to know. And sigma sub x bar is equal to what they want to know. So what is mu sub x bar here and why? You need to explain it to me. What is mu sub x bar? Anyone?
Is it 25?
25 is the sample size,
Oh,
not the average. What is mu sub x bar? That means mean of the sampling distribution. Mu sub x bar is the mean of the sampling distribution. What is it?
isn't it 50?
Why? Yes, it is 50, but why?
Isn't it because it's like it was like one of the first part told us that it's I don't know how to explain it, but you told it was like the first thing you told us that was it mu of x bar equals the mu?
Yes, absolutely. You're right. One of the conclusions of central limit theorem is that mu sub x bar is equal to mu, which is absolutely right. So that's why we can say that mu sub x bar is equal to 50 because mu is 50. However, there is a catch though. The catch is that we said that this is going to be true only if sample size is greater than or equal to 30, but my sample size is 25. Is there a problem?
Yeah, it's less than 30.
So maybe if it is less than 30, I shouldn't be concluding that this is equal to that. So my conclusion is incorrect. It's less than 30. So my conclusion.
Of sigma x bar.
Yes, what's up with that?
So we're just going to use the new sample, the 25.
Yeah, sample size of 25. But the question is, let me clarify the question again. This is true if your sample size is greater than or equal to 30. This is true. And so is this one. Sigma sub x bar is equal to sigma divided by square root of n. This is true so long sample size is greater than or equal to 30. Sample size is 30 or more. But my sample size is 25. So how can I use these conclusions?
We're just going to plug in the equation. So 30 over 25.
Yeah, I know. I'm not even there. You're just jumping ahead. That's how you'd find sigma sub x bar. But I have even more of a fundamental question. If I can apply these two rules only if sample size is greater than or equal to 30, I should not be even applying it, let alone doing the calculation, because my sample size is 25, which is less than 30. So why am I doing it? So am I making a mistake or what's going on? Okay, George has the right response. See, I can, even though my sample size is less than 30, which is 25, I can still conclude these two things. Why? Because the initial population is bell-shaped. I'm sampling from where? I'm taking samples of size 25 from where? From this population. This population is bell-shaped. So it doesn't matter what the sample size is. Sampling distribution is always going to be bell-shaped. That is the reason. It really doesn't matter what the sample size is. the sampling distribution is always going to be bell-shaped because my original population from which I'm sampling, it has bell-shaped. That's the reason. So why is it 50? Because even though sample size is less than 30, it is 50 because the original population has normal distribution or Gaussian distribution. Now, if that is the case, then we could accept this one too, which someone was calculating sigma sub x bar is going to be equal to sigma, which is 30. Okay, 30 divided by square root of the sample size, which is 25. So 30 over square root of 25 is 5. That's going to give you 6 because 5 goes into 30 6 times. So sigma sub x bar is equal to 6. And you can see this has a lower standard deviation, means this graph should be narrower, bell-shaped yet narrower. That means data points here in this distribution are more closer to the mean than the data points in this distribution. These are two different distributions, remember. One is with sample size of 1, which is just the natural sample size. The other is a sample size of 25, which is not a natural one, but we made it up. Okay. Any question on this, anybody? Okay, find the probability that a randomly selected person spends more than 110 minutes on the social media. So find the probability that a randomly selected person spends more than 120 minutes, 10 minutes on the social media. That means X. So find the probability that a randomly selected person, A means 1, right? A randomly selected person. So when we are talking about 1 sample size, that means we are in this graph. When we are talking about more than 1, then we are in this graph. So you really need to know which graph are you addressing. You need to figure out which graph are you addressing. Are you addressing the population graph, or are you addressing the sampling distribution graph? In this case, it says find the probability that a randomly selected person spends more than 110 minutes. So greater than 110. So it's easy. You have to just find the corresponding value 0, 1, standard normal distribution. Okay. So what point? So 110 is probably somewhere here. So you want more than, meaning what? That area. So now I have to translate that to the corresponding z value here. Okay. So we know how to translate. Z is equal to x minus mu over sigma, which is x is 110 minus mu is 50 over sigma is 30. So which is 70 over 30, which is approximately 2.33, right? So that's the same as probability of z greater than or equal to, or greater than, doesn't matter, the same thing, right? 2.33. Now, that's the area I am talking about. However, the problem is that the table, standard normal distribution table, does not give you that area. If I look at z is equal to 2.33, if I look at z is equal to 2.33, then we are going to get the area to the left of that point. All the area, cumulative area to the left, but we need the area to the right, which is the complement. So we can just go ahead and do it. 1 minus the probability of z less than 2.33. Now we need to be able to find that value. So in my last class, I have noticed that some people still don't know how to look it up on the table. Please make sure that you do. Okay. So let me bring the table back here.
I got a question.
Yes.
Wouldn't 110 minus 50 be 60? Wouldn't the z-score be 2?
Is it 110? Did I make a mistake? Possible. Hold on. Oh, yeah. Why was I thinking 120? For some reason, it's, oh, okay, I changed it from last time, I forgot. Okay, so that'd be 60. Thank you very much. So that'd be just 2. You're correct. Is equal to 2. So that's gonna change this guy to 2. And this guy to just 2. This guy to just 2. There you go. Thank you. So let's look it up in the table, okay? So 2, positive z scores 2. So you look in the first column. So everybody, you look at the first column. You look it up in the first column and you get to 2 right here. Okay. And 0, 0 is the, so then you look at through the first row. And if it is 2.33, you 2.03, you're gonna go there. If it's 2.05, you're gonna go there. So in our case, 2.00, so it's gonna be 0.9772. 0.9772. So let's go ahead and bring that back. So it's gonna be 1 minus 0.9772 is equal to 0.0228, or there is 2.28% chance that a randomly selected person would spend more than 110 minutes in the social media. Next problem is that find the probability that 25 randomly selected persons spend more than 120 minutes in the social media. Okay, I'm gonna change it a little bit here. Let me just go ahead and change it. I want to keep it the same level. Hold on. Okay. Okay, all right, there you go. Find the probability that, I meant to say 110. So I changed it, but you won't see the change because I want to keep both of these numbers the same. X greater than 120. Now find the probability that X bar, the average of 25 people, is greater than 120, I mean 110, okay? So 110 will be somewhere here, 110, because we are talking about the average. So we must be looking at the sampling distribution, which is this one, right? Sampling distribution. And that is gonna be this area. So now we need to go ahead and find the corresponding Z value. Remember, sigma sub X bar is 6 here. So what is the Z value? Z is not going to be Z anymore. It's going to be Z sub X bar, just to indicate that we are dealing with sampling distribution. Z sub X bar is equal to, so this is actually X bar. And if we draw another graph, this has mu sub X bar is equal to 0 and sigma sub X bar is equal to 1. So now corresponding to this point, there will be a corresponding Z value here, which is Z sub X bar. And we need to find that. Z sub X, like the way we did here. Only difference is that we call it Z sub X bar as opposed to Z. So now Z sub X bar is going to be X bar minus mu sub X bar divided by sigma sub X bar. Sigma sub X bar is 6. So just put it there. X bar is the point in question, 110. Minus mu sub x bar is the average, which is 50. There's gonna be 110 minus 50 is equal to 60 over 6, which is 10. So your z sub x bar is equal to 10. So probability of x greater than 110 is the same as the probability of z sub x bar greater than 10, which is 10 standard deviations away, which is crazy amount of distortion or crazy amount away from the mean. So that is going to be the 1 minus probability of z sub x bar less than 10. 1 minus probability of z sub x bar less than 10. Okay. Now
We gotta plug it into the z table for 10.
yes, you got to plug it
And
into the z.
And isn't it like true that like I could be wrong, but isn't it true that 3.5 or higher, it's always going to be 0.99999?
Yeah.
Oh,
So if
okay.
you look it up in the table, let me take this away and bring the table. If you look at the z table, this is the positive z value. The highest value it goes to is 3.5. But our z, that's the highest value. But our z is 10. It's a way off the chart. So it's probably going to be not 0.99. It's going to be probably 0.9999 and then maybe a few more nines. Okay. So that's what it's going to be. So let's bring back the stuff. So it's going to be approximately 1 minus 0.999999, maybe a couple more. Okay. And which is very, very close to 0.00034567, maybe something like that, 7 or 8 zeros. One. And these numbers are made up for me, these two, because since this is off the table, okay, off the chart, I don't know what it is, because this one is made up, means this one is made up too. The point here is that it's extremely low chances, so it's not the actual number in and of itself. The probability that one person spends more than 110 minutes in the social media is not that high, but still it's not bad exactly. It is, by the way, where was it? Where did I do it? Yeah, it's right here, about 2.28%. So the probability that if I were to select a person randomly from the street, okay, the probability that that person spends more than 110 minutes on the social media is about 2.28%. Now, on the other hand, if I take randomly 25 people from the society and find the average of their social media spend time, I find that that average, the probability of that average being more than 110, look, the same number, 110 here and 110 here. The probability of their average being more than 110 is extremely small or very, very unlikely. It's probably not going to happen in under normal circumstances. That's what it is. Is it okay, guys?
Yeah, it's pretty straightforward.
Okay.
How come just one question. How come if how come it's 3.5 or higher, it would always be the same number? Is it because like it reached all the way to its maximum whatchamacallit, maximum how many numbers they can put, like that's how much they can put, 3.5 or higher?
So z value of 3.5 is pretty high in a normal distribution. In theory, z goes to positive infinity and z goes to negative infinity. But the probabilities fall off so quickly that it's insignificant, okay? So at 3.5 z score, your z value is 0.9999, which is literally 100% almost, right? So
Yeah.
Going 10 standard deviation as opposed to 3.5 would make it even further smaller, or bigger rather, further bigger, which is consequently subtracted from 1 is further smaller. So yeah, since there is no value for in the table for 3.5 or above, you can just take 3.5. Okay, 0.9999.
Okay. Thank you. Good to know.
You're welcome. Okay. Now the next question is, find the probability that a randomly selected person spends between 40 and 60 minutes. So in that problem, are we in this situation or in this situation? Find the probability that a randomly selected person spends between 40 and 60 minutes. Which scenario are we dealing with? The top one or the bottom one, left? We are dealing with the top one on the left, because probability of a randomly selected person. It didn't say the average or with a sample of 25 or 30. So it's the probability that a randomly selected person. So probability that a randomly selected person spends between 40 and 60 minutes, right? Again, my sample size is 1. That means I'm in the population. So 50 is the mu. So 50 to 60 here, 50 to 40 here. Probability between these two is gonna be just this. All right. Now we need to convert it into standard normal distribution. You can see mu is equal to 0 and sigma is 1. I'm gonna be here and here. I'm not gonna do it really, just maybe do one. Z is equal to x minus mu over sigma. You can just do the 40. X is 40 minus 50 over sigma. Sigma is, 30. So put the 30, which is negative 10 over 30, which is negative 0.33. All right, approximately. So this is negative 0.33, and this is gonna be by symmetry positive 33. And then this and this. So this is the area that I'm looking for. And so probability of x being between 40 and 60, between 40 and 60, is the same as the probability of z being between negative 0.33 and 0.33. Now, to find the area associated with this, in between, you have to keep in mind, this is 0.33. If you look it up in the table, okay, for 0.33, so let's go ahead and look it up in the table for 0.33. You'll see 0.33 is right here. So 0.3, so 0.3 right here and 0.03 right here, and they intersect right here, 0.6293. So probability of z less than 0.33 is 0.6293. Okay. Okay. So this is the same as probability of z less than 0.33, which is going to be giving you all the area to the left, but you don't want this area, the unshaded region. So you have to subtract that from it. And remember, if you look at the probability of z less than negative 0.33, probability of z less than negative 0.33, then you're going to be looking at only the unshaded region, okay? So what was the value? 0.696293. So this was 0.6293. minus the probability of z less than negative 0.33. So let's go to less than negative 0.33. So let's look it up. Negative 0.33 is right here. Slightly above 0.3, negative 0.33, 0.3707, okay? Point 3707. So 0.6293, 0.6293 minus 0.3707 is 0.2586. Is 0.2586, which is, by the way, 25.86%. So there is a 25.86% chance that an individual would spend between 40 and 60 minutes. Now let's go ahead and do the exact same problem for 25 people. Their average, n is equal to 25. Unlike this one, where n is 1. So this time we are doing for 25 people. So it's going to be narrower curve, just to give you a heads up. So mu sub x bar and sigma sub x bar. And we have to convert it into standard normal distribution, which is 0, mean mu sub x bar is 0 and sigma sub x bar is equal to 1. Now to go back and forth between these two, we're going to use z sub x bar is equal to x bar minus mu sub x bar over sigma sub x bar. So it's going to be mu sub x bar is 50, as you know, by the central limit theorem. So this is 40 and this is 60. So we are looking for the probability that 40 is less than x bar. That means the average of these people is in between 40 and 60. Now we have to convert the 40 and 60, but of course we need to know that 40 and 60, this is the area we are looking for, right? This is the area we are looking for. Now what does 40 translate to here? So let's go ahead and do z sub x bar is equal to x bar minus mu sub x bar over sigma sub x bar. So x bar is the point in question, which is 40. 40 minus mu sub x bar is 50 divided by sigma sub x bar is 6. Remember, sigma sub x bar, we found it 6. So 6 is going to be negative 10 over 6, or z sub x bar is equal to approximately negative 1.67. So this is negative 1.67. And by symmetry, for 60 is going to be positive 1.67. So now you're going to have to find these two areas. So probability of z x bar between 40 and 60 is the same as the probability of z sub x bar between negative 1.67, okay, negative 1.67 and positive 1.67. That, by the way, is the same as probability of z sub x bar less than 1.67 minus the probability of z sub x bar less than 1.67. Now you need to find these probabilities for z sub x bar equal to 1.67. So let's bring the table back. Negative 1.67. So negative 1. So look at the z column right here. Negative 1.67. So negative 1.6 right here. And for 7, we are going to be going right here. Oh, there's the negative 0.0475. 0.0475 for the negative one. So there's going to be equal to negative 0.0. So by the way, this should be negative 0.0475. Now we got to find it for positive 1.67. I just found negative 1.67. So again, let's go ahead and find the positive value. This is the negative z-score table. Let's just look at the positive z-score table. 1.67. So 1.6 right here. And 7 right here. So am I on the right row? Okay, 1.67, yeah, 0.9525. 0.9525. So 0.9525 minus 0.0475 is 0.905 is equal to 0.905, which is, by the way, 90.5%. There is a 90.5% chance that average of 25 people would fall between 40 and 60. Compare this with the individual case. For the individual, the score could fluctuate a lot. Okay, I mean the time spent. So for an individual, it is 25.86%. But for a group of 25 people, the same interval would give you a probability of 90.5%. So that's the difference. The central limit theorem allows us to squeeze the data points and get information about the populations, okay, mean, and obviously standard deviation as well. Any question, anybody?
No.
I don't think so. I think I'm fine.
Okay. Now I'm gonna give you an opportunity to work on this. I'm gonna even leave the screen on here. Everybody do the CLT example 2, which is slide number 131. Okay. CLT example 2, slide number 132. Mr. Zach, the founder of Facebook, recently announced that average person spends 60 minutes as opposed to 60 minutes per day on social media. Standard deviation is 30 minutes and assume bell-shape, and answer these questions. What I'm gonna do, I'm gonna break it down into pieces. So go ahead and answer the first maybe 2 questions. Okay, what is the standard deviation? Hold on. No, first 4 questions. Answer the first 4 questions, everybody. First 2 should be easy, just one-liner. And the second 2 should be slightly more complicated. So I'll give you about 7 minutes to work on it, but I want you to work on it. And I'm gonna be asking you randomly, okay? So make sure that you work on it. Unless you do it by hand, you're not gonna learn it by me working on it. It's like biking. You know, I know how to bike and you don't know how to. So you look at me, oh yeah, it's so nice to bike. It's so easy. But unless you get on the bike and you start trying it on your own, and then you fall, you get hurt, and you realize that, oh, it's not that easy. Okay. I have done these things many times, so I can do it naturally because I have seen it many times. However, you are seeing it for the first time, so it's difficult for you. So I want you to try it by hand. Everybody get a piece of paper and work on it. Okay? Get a piece of paper and work on it. And then I'm gonna be asking you how you did and whatnot. All right. So take a few minutes, 5 to 7 minutes, and then do the first 4 problems. Thank you. So they tell you the following. The mean is for the population, the mean is 60, I think, and standard deviation is sigma 30. So that's your mu, and standard deviation 30. Now, so you take a sample of size 25. So this is for sample of size 1, n is equal to 1, which is the population distribution. So make sure that you understand the distinction between population distribution and sampling distribution. So now if you take a sample of size 25 and you create, you consider the sampling distribution, okay, is gonna be looking like this. All right, this is mu sub x bar, and this is sigma sub x bar. And since the initial population is bell-shaped, the sampling distribution, I mean, sample size does not matter, okay? The sample size could be anything. It would still be normal distribution or bell-shaped for sampling distribution, because the initial population from which you are sampling, it has bell-shaped or normal distribution. So now, what is the, so if you take a sample of 20, use the social media, then what is the average of the sampling distribution with sample size of 25? So that means they're asking you, what is mu sub x bar? So let's answer these questions one by one. What is mu sub x bar? What is it and why?
Is it 60?
Who is talking?
Tyler?
Tyler. Why 60?
Because even though, well, because both of the graphs are bell shaped, so it doesn't matter.
No, that's not the reason. Because it is 60 because the sampling distribution is bell-shaped according to the central limit theorem. And the central limit theorem gives you two tools. One of the tools is mu sub x bar is equal to mu. If mu sub x bar is equal to mu, but we know mu is 60, so mu sub x bar is also what? 60. That's the reason.
Oh, okay, thank you.
Now, next question. What is sigma sub x bar? What is it?
Six.
Yeah, that hasn't changed really, because sigma sub x bar according to the central limit theorem is sigma divided by square root of the sample size. Sigma is still 30. Okay, sigma is still 30 divided by sample size is still 25, which is 30 over 5, which is 6. So sigma sub x bar is 6. Number 3. All right. What is, so what's the third question? Find the probability that a randomly selected person spends more than 120 minutes on the social media, which is easy. Probability that X greater than 120. Now, a randomly selected person, remember that, a randomly selected person, just one person that we are talking about. We are talking about just a single person, a randomly selected person. Now, does it belong to, are we talking about this graph or we are talking about this graph? Which one are we talking about? Top one or the bottom one? And why? Are we talking about the top one or the bottom one? Why? Anybody? It's one person, right? X, it relates to only one person. So sample size is 1. So it's the population that we are talking about. So 120 is going to be somewhere here, and we are looking for the area to the right. And we just have to do the same thing that we did before. We have to convert it into a standard normal distribution, right? With a mean of 0, standard deviation of 1, and it's going to give you z-score of 2, by the way. We know that. So it's the same as the probability of z greater than 2, which is the same as 1 minus the probability of z less than 2, which is 1 minus 0.9772, which is 0.0228. That is the same as 2.28%. Okay, it's the same as 2.28%. Now, the next question, find the probability that a randomly selected person, find the probability that 25 randomly selected persons spend more than 66 minutes on the social media. So 25 randomly selected persons, so n is equal to 25. Whenever you are writing these problems, you kind of want to write down the sample size. Here n is equal to 1, here n is equal to 25. So that means right away you're dealing with sampling distribution, which is this one, because here n is equal to 25. It takes a bit of time, guys, to get the hang of it. And you have to just keep trying and trying. Okay, it's not an easy concept. I remember my struggling days when I was learning these things as a student. It didn't make any sense to me. And of course, my teacher was very nice, but didn't handhold. He was very nice, but still, I needed more help. Okay, and these topics take a little bit of time to get a feel for and get a kind of grasp of what we are talking about. Like I struggled with the concept of sampling distribution for a while, and then consequently, if you have problem understanding sampling distribution, you won't understand central limit theorem, which is fundamental. So it takes a little bit of time to sink in, and please be patient and keep trying. So n is 25, which means we are talking about the sampling distribution, which is this one, that has mean mu sub x bar and sigma standard deviation sigma sub x bar. So we want to find out the probability that a randomly selected person, spends more than 66 minutes, okay? So we know that this is 60 from here, right? Mu sub x bar, 66 minutes. Now, on purpose, I made a mistake here. What is the mistake? Anybody knows? I made a mistake here. What is it?
You should say that says greater than instead of less than.
Did it say less than? No, it's less, greater than, more than, greater than, but that's not the mistake. There is no mistake there.
You were supposed to put X bar instead of X.
Who is talking?
Jessica?
Good, thank you, Jessica. I'm supposed to put X bar instead of X because X applies to only one person, but X bar applies to more than one person. Or X applies to only one entity. X bar applies to more than one entity. So it's X bar greater than 66. If you do the translation, you will see again, mu sub X bar is equal to 0 and sigma sub X bar is equal to 1. So the Z sub X bar is gonna be X bar minus mu sub X bar over sigma sub X bar. So sigma sub X bar is 6, which you also found here. And X bar is the point in question, which is 66. Okay? So 66 minus mu sub X bar, which is 60. 6 over 6 is equal to 1. So probability of X bar greater than 66 is the same as the probability of Z sub X bar being greater than 1, which by the way is the same as 1 minus the probability of z sub x bar is less than 1. Okay, which is 1 minus point, you can look it up in the table, 0.8413, I believe, 8413, which is 0.1587. That is 15.87% chance. There's a 15.87% chance that somebody would, average of 25 people would be greater than 66 minutes. Okay. And this is z is equal to 1. Z sub x bar, since we are talking about sampling distribution. And this graph isn't quite representative of 15%, but it's okay, you get the idea. This shaded region is 15.87%. Okay, so probability that average of 25 people is more than 66 minutes is about 15.87, or roughly about 16%, you can say. And that is what it is. Any question, anybody? Are these two concepts okay, everyone?
Yeah, I
much
think it's all
better
right.
this week.
Explains everything. Explains the stuff pretty well.
Anybody else?
I will probably have to keep practicing.
I think that's a good idea. You need to practice these problems a bit more than usual. Okay, now try the last two, okay? Try the last two examples on the same slide number 133, last two. Probability that, so I'm even gonna write it here. You need to find the probability that a randomly selected person spends between 30 and 60 minutes. 30 and 90 minutes. And find the probability that average of 25 people, okay? 25 randomly selected persons spend between 54 and 66. 54 is less than x bar is less than 66. This one applies to population. This one applies to sampling distribution. Here n is equal to 1 and here n is equal to 25. I'm giving away the answer almost. Please do these problems by writing on paper, because these are problems that you need to understand. You will need to solve them in the midterm. You'll need to solve them also on the homework and also on the final. So please pay attention, okay? All right, so I'll give you 5 minutes or so. So probability of x being between 30 and 90 is the same as the probability of z being between -1 and +1. So for 30, we did the calculation here. Z is equal to x minus mu over sigma. So 30 is x, mu is 60, which is this guy, divided by standard deviation, which is 30. So 30 minus 60 is -30. Over 30 is -1. So that's how I got this -1. Now, if you do the same calculation exactly, but replace this x by 90, you're gonna get +1. Now, there's gonna be this area in between, and we know how to find the area between two z values. So it's gonna be probability of z less than 1 minus the probability of z less than -1, okay? Which, by the way, is the same as, so probability z less than 1 is 0.8413 minus probability of z less than -1 is 0.1587. If you do the math, it comes out to 0.6826, which is the same as 68.26%. 68.26%. That's the same as 68.26%. Okay. Now, there is a reason for me to give this problem, okay? And you'll see the numbers are designed in such a way so that you can really get a feel for what's going on. Now, for the other one, it is between 54 and 66. This one is between 30 and 90. For a single person or for the population's distribution, to jump between 30 and 90 is like jumping between -1 and +1, meaning you are jumping 1 standard deviation to the right and 1 standard deviation to the left. Exact equivalent move in the sampling distribution would be going between 54 and 66, because from mean is 60, right? From mean, if you move 1 standard deviation to the left, that's going to 54 because your standard deviation is 6, right? If you move 1 standard deviation to the right, it's going to be 66. And now let me go ahead and do these calculations because you guys are likely to mix it up. So here is going to be z sub x bar. Z sub x bar is equal to x bar minus mu sub x bar over sigma sub x bar. That's the formula we are going to be using. And I'm going to draw a small little graph here in the bottom left. So this is your 0 and this is your 1. And this point is going to correspond to 66, okay? And this point is going to correspond to 54. So we are looking for the area in between. That means this, okay? And if you do the math, you'll see, so z sub x bar is equal to x bar is, let's say 54, that's the one we are doing first, minus mean is 60 divided by standard deviation is 6, which is going to give you -1. So that's -1. And if you do the exact same calculation for the other one, z sub x bar is equal to x bar is 66 minus 60 divided by 6 is just 1. So this is 1. So the probability, so this is 54, let's say this is 66, 54. And I am going to be looking at, okay, actually, yeah, oh, maybe not. This is actually 66 right here, this particular line. And this is 54. And I'm going to be looking at this here. This is symmetric, even though I'm graphing, sketching it. So I'm human, right? So I can be precise. So that's the area we are looking for. So that's the same as saying probability of z sub x bar between z sub x bar. Look, not z, like the way we had z here. It's not z anymore. It's z sub x bar for the sampling distribution between -1 and +1. The same as the probability of z sub x bar is less than 1 minus the probability of z sub x bar less than -1, okay? Now, this is 0.8413 minus this is 0.1587, and it comes out to be 0.6826, which is 68.26%. This is what we are talking about. All right, both of them. So for you to have a 68% chance roughly in the sampling distribution, you just have to move a little bit, go from 60 to 54 and 60 to 66. Okay, it's very sensitive. On the other hand, you have to move a lot in the regular population. So you have to go between 30 and 90 versus 54 and 66. Both of them have the same probability. So why is this happening? Because of this standard deviation. In the sampling distribution, the standard deviation is, by the way, smaller, much smaller than what it is in the original population. Okay? In the sampling distribution, the standard deviation is much smaller, meaning that the data points are closer to the mean or hugging the mean more closely or more concentrated around the mean. On the other hand, in the regular population, the data points are kind of spread out with respect to the mean or with respect to the center of the data set. Any question, anybody?
No, I think I'm good.
Everybody okay?
Yeah.
All right, in that case, what I'm gonna do, I'm gonna give you some assignment. I gave it to my other class, so I'm gonna give you guys an assignment. Because this stuff needs, in addition to the online homework, I want everybody to work on this problem and bring it to the class on Monday. Okay, today is Wednesday, so next time we're gonna meet is on Monday. I'm gonna send you a Google Drive, all right? I'm gonna send you a Google Drive, and then what's gonna happen is that you're gonna upload it in the PDF format. All right, you're gonna go to the Google Drive and upload the PDF format. So if you, the way to do it is, if you don't have a PDF converter, what you want to do is write the problem on a piece of paper, work on it, and then go ahead and take a picture of it and then upload the picture online and convert it into a PDF file. There should be a way to convert to PDF, or maybe your iPhones or cell phones give you an option to save it as PDF. Does it give you that option? Save an image as PDF?
You can.
Does it?
You
You
can
can?
through the notes. Yes, through if you have an iPhone, you can do it through the notes. You can upload a PDF file and just download it to your files, and you can do it that way.
Not upload. So if I take a picture with my iPhone, right? Then can I convert this picture image into a PDF file?
Yes, through the notes.
So you have to upload the image to the notes and then save it as a PDF and
Yes,
download.
it gives you the option to upload the photo as a PDF file.
Oh, it does?
Yes.
I don't use notes really very often. So let me see if I can do it while you're on the phone.
You can also just attach the image in an email to you and it will come out just the same and you should still be able to view it.
No, sometimes it's a problem, and there's also whoever is saying, I don't mean to be kind of putting you on the spot. That's the old school way of doing things. Nowadays, people use Drive to share files.
So we're not doing it on Canvas then? It's only on the Google Drive.
I'm trying to get my note. Okay, where is my notes? I can't find my note.
So do you want us to like upload it on our Google Drive and then just share it with you?
Yeah, I'll give you a link to a Google Drive and you just upload it. Then it'll automatically be shared with me.
Okay.
Okay. So
All
the
right.
problem number one, let me write it down. Problem number one, the average number of hours that the college students in the US study is 17 hours with a standard deviation sigma. Let's make it 3 hours. Okay. And we are assuming that it's normal or bell-shaped. The distribution of the hours that students study is bell-shaped. So based on this, answer the following questions. Number one, find the probability that X is greater than, so part A, 1A. Find the probability that X is greater than 18. Then find the probability that X is less than 15. Then find the probability that X is between 15 and 18. Part B, if n is equal to, let's keep it simple. No, not this. If n is equal to 16, it's still simple. Do the exact same thing. Find the probability that x bar is greater than 18, probability that x bar is less than 15, find the probability that 15 is less than x bar is less than 18. Okay, that's number one. Then number two, again, the same thing. Mu is equal to 17. Sigma is equal to 3. But this time, I don't tell you whether it's bell-shaped. Let's assume that we don't know the distribution. So now part A, consider n sample size is equal to 25. Okay. And answer these questions. Probability of x greater than 18. Probability of x less than 15. Probability of 15 is less than x is less than 18. B, for n is equal to 49. Again, answer the same questions. Probability of x greater than 18. Probability of x less than 15. Probability of 15. Oops, I made a mistake here. This is x bar, and x bar. Sorry about that. Probability of x bar 15 is less than x bar is less than 18. And these few questions everybody has to answer, and then take picture, very clear picture, and write it clearly, nicely, not some scribbling. Draw the diagrams and identify the appropriate regions and then shade them, and then clearly write down everything the way I write down in the class. And then do these problems and upload your work with your name on the top right corner, okay? Print your name, not like Maria, not that. When I say Maria, printing means this, M-A-R-I-A, Maria Sanchez. Okay, something like that. Okay, that's what I want you to do. And then I look at your work because I really need to see that you guys understand these topics. This is fundamental, all right? And any question, anybody?
Is the Google Drive the one that you gave us
No.
for?
I think in that one, you can't upload anything. I think you just have view permission. I'm gonna create another Google Drive and I'm gonna give you permission there to upload things. So you'll be able to upload things there.
Are you just gonna email it to us?
Yes, I'm gonna email it to you by the weekend so that you can have it ready.
All right. All right. Thank you. And it's
Any
only
other
these two. Only these two problems. There's no third one.
No, these two problems, and there are actually 4 parts to it. So there's good amount of work. Okay.
Thank you. Have a good one.
And I have recorded this session, so I'll be sending it to you as well. So you can go ahead and look at it. All right.
All right.
All right. That's all for the day. Thank you so very much, guys. You have a wonderful day and rest of the week and
When
weekend.
do we have to upload the answer?
Before the class on Monday.
Oh, okay. Okay, thank you.
Okay.
Have a good one. Bye.
Thank you.
Thank you. Bye.